the focus of this unit is going to be identities, and we're going to focus on several different kinds. And these are basically proven relationships between trig functions, so some patterns that we see that are easy to use to help us manipulate things. So if somebody asked us something in one form and we couldn't quite figure it out, we could manipulate it by changing it into another form, like thinking of 2 as 1 plus 1, that knowing that those are the same things, except for that this is with trig functions. So through each unit here, at least through the first 3 lessons, we're going to add a lot of identities. You might want to keep like one sheet of all the identities you're using because they'll come in handy when you're trying to do your proofs. So we're going to go through some things here. Cotangent, just a reminder, is the reciprocal of the tangent. Secant is the reciprocal of the cosine. And cosecant is the reciprocal of the sine. So this means anytime somebody talks about cosecant, I can use a cosecant in what I'm working on, or I could rewrite it as 1 over sine if that becomes simpler for me to do. The tangent, since it was like y over x and y was like the sine, could also be thought of as sine over cosine, which means there's actually several different ways for us to think of the cotangent. It could be 1 over tangent. It could be cosine over sine. So we're just saying that all these things can be written in these different ways. And our first lesson, or throughout the first 3 lessons, sometimes you'll be asked to do a calculation, but a lot of times we're asking you to either prove that something can be rewritten in a different format or to simplify something as simple as possible. So I want to remind you what simplify means. And so here's something we're more familiar with, 1 plus 3 over x. To simplify something like 1 plus 3 over x would be to combine it into one fraction. So I would think of 1 as x over x to make the common denominator. And then I could now write this as one fraction, and this would be considered simplifying that because it combined 2 different terms into one term. So simplifying is trying to create one fraction if fractions exist, and then to reduce that fraction or rewrite that fraction in the simplest form. Here is something that we're not used to seeing, something like sine squared plus cosine squared, and our original reaction to this would probably be that it's already simplified, but we're going to start to think about this in a little bit of a different perspective. We know on the unit circle that we can use that in relationship to these trig functions, just like any circle. And if you did have something here and this is your point x, y, then you would be able to say, using distance formula or Pythagorean theorem, that x squared plus y squared should be equal to r squared, but we know that the radius is 1. So x squared plus y squared is 1. But in the unit circle, x can be replaced with cosine and y can be replaced with sine of the angle that's there. So this means that we could rewrite this statement as sine squared theta plus cosine squared theta equals 1. And that means that this statement right here can actually be simplified to be 1. So this brings us to our first identity that's super handy for us to use. And that is basically the identity that came straight from that Pythagorean theorem. And there's kind of 3 different versions of it dealing with different trig functions. So the first one that you saw there is that if you have cosine squared plus sine squared, that equals 1. Okay, cosine plus sine does not equal 1, but cosine squared plus sine squared could equal 1. And then I want you guys to get used to manipulating this. So knowing that cosine squared plus sine squared equals 1 also means, since you know 2 things are equal, you can move things from side to side. If you're trying to prove things are equal, you can't. But this is something we now know is equal. We could write it in this different format. We could then say this means that we know every time we see sine squared, if we wanted to, we could replace it with 1 minus cosine squared. Or using the same arithmetic, if we had kept the cosine squared but canceled out the sine squared, we would have a statement that says cosine squared theta equals 1 minus sine squared theta. So you can go through and you can do the same thing with tangents and other relationships. So another version of this Pythagorean theorem relationship, another thing you can find strictly through the Pythagorean triangle relationship, is that 1 plus tangent squared ends up equaling secant squared. And again, you could rearrange pieces of that. And you also can end up finding 1 plus cotangent squared equals cosecant squared. These should be on your list of formulas that you're going to use. Now, in example 1, we're going to actually prove this last formula correct. However, anything that we've given you as an identity, you can use in the future. You won't have to prove it, but here we're asking you specifically to show us that this works. So this is like a proof, and we're going to ask you guys to work on one side, mostly because the error that people make here is they want to do something like this. They want to subtract 1 from both sides. And the reason that you can't do that is this subtracting 1 from both sides, the name of what you're doing when you solve equations and you do anything to both sides, is like the subtraction property of equality, meaning you're only allowed to do this because you know these things are equal. But this problem doesn't say here's an equation that we know is equal. It is saying show that these are equal. So you don't get to assume they're equal and move things from side to side. So I'm going to pick one side of the equation to work on. I often pick the side where I feel like I can start working, like there's something for me to do. So for me in this problem, that would be the left side. And the reason it would be the left side is because I know that I can think of the cotangent as a fraction. And then that means that I can think of 1 as a fraction, and I can try and put the fractions together like we did in the simplifying problem. So I'm going to rewrite cotangent. So this is all about manipulation. As a fraction. So I'm specifically going to write cotangent as cosine over sine. And because the cotangent was squared, the cosine squared, and so is the sine. I'm not doing anything to the right side. So my next step, and how would I know I want to combine these together? My ultimate goal is to make it look the same as the right side, and the right side is one simple trig function. So I know that on the left side, I want to try and combine everything together. So I want to try and add these two together. So I'm going to rewrite 1 so that it has a common denominator with the other fraction whose denominator is sine squared. So I'm going to choose to rewrite 1 as sine squared over sine squared. And now I have fractions with a common denominator, which now means I can combine those fractions into 1. So this is going to become 1 fraction where the denominator is sine squared, and the numerator is going to say sine squared plus cosine squared. And this is where knowing your identities would come in handy. We should recognize sine squared plus cosine squared. It was on our list of identities. Sine squared plus cosine squared is equal to 1. So I can change that to a 1 because that's something equivalent. And 1 over sine is the same as cosecant, so I can now rewrite that as cosecant, and I've proven that it's the same as the other side of the equation. So the proof here is not like geometry. You're not making a step and writing a reason, but it is like geometry in the effect here that you have a beginning, the side you're working on, and you do have an end goal. You are trying to prove it is the same as this. And you can't break any mathematical rules, and you can't use properties of equalities. Okay, you can't do things to both sides of the equation because you don't yet know that they're equal. So example 2 says verify the identity. So again, this is the same thing as showing two things are equal or writing a proof. You're verifying. So you don't get to assume they're equal. You cannot add, subtract, multiply, or divide what you want to both sides of this equation. You need to pick one side and work on it. So I'm going to pick the left side because I see a multiplication problem that might simplify and leave me with this single thing that I see on the right side. So the first thing I'm going to do on the left side, the first thing that stands out to me is I do have a different way of writing cotangent. I can write it as cosine over sine. I'm not going to write the right side, and you guys can do the same. I'm going to put the equal sign so you know which side I'm working on. And I'm just never going to change the side I'm not working on, so I'm just going to keep it till the end. Here, you can see that the signs would cancel out, and you would be left with cosine theta. So that proof only had that one step in between, and then we got to the fact that those two things are equal. So part B says the same thing. We're doing a proof here. Oh yeah, I missed it. Okay. So part B says we're verifying these things are true. So I'm going to pick one side. And again, I'm going to pick the left side because this side to me is more difficult. If I wanted to do stuff to that side, I would have to start multiplying in extra things. For my brain, that's a little harder to figure out than simplifying. So I try to pick a more complicated side that I think I can simplify. So I'm picking this. So notice the numerator here, 1 minus cosine squared. What you want to do is notice that that looks similar to something you know. You know sine squared, cosine squared, and 1 are all involved in an identity. So if I remember that sine squared plus cosine squared equals 1, if I subtract cosine squared from both sides, I have that sine squared is equal to 1 minus cosine squared. So this 1 minus cosine squared can be replaced with sine squared. Now, sine squared and sine, if you're having a hard time understanding the squares, that's a sine theta times another sine theta in the numerator. And in the denominator, you have one sine theta. So one sine from the denominator will cancel one of the factors from the numerator. And so when we cancel that out, that will just be sine theta, and that matches what's on the right side, and I verified that that is true. So now I'm going to look at part C. And there's not a right or wrong answer. So if you paused this and took this on yourself, which you can do right now, you can pause the video and try it yourself. If you did it differently than me, that is not incorrect. It may take more steps, it may take less steps, okay? As long as you aren't incorrectly using identities or using some properties that can't be assumed here, then you're fine. I'm again going to choose the left side because I think it'll be easier to simplify. And the first thing I'm going to do is rewrite secant as 1 over cosine. So I'm going to have sine squared theta times 1 over cosine theta plus cosine theta. So nothing cancels out, so that didn't work that great. But so right now I have a fraction. I'm going to write this as 1 fraction plus another term. And I'm trying to combine them into one thing. So my focus is now going to be to write this cosine term as a fraction. So right now it's like it has a 1 in the denominator. I'm going to rewrite it with a cosine in the denominator. So as I rewrite it, what I'm really doing here, and I wouldn't necessarily need to see you write this step because I would understand the next one, but I know for some of us this can be difficult to see. I'm basically multiplying top and bottom of that by cosine so that my next step looks like sine squared theta over cosine theta plus cosine squared theta over cosine theta. Now that they have a common denominator, I can write them as 1 fraction. So the denominator is cosine. The numerator has sine squared plus cosine squared. And I would recognize that as my identity that says sine squared plus cosine squared is 1. And 1 over cosine theta can be rewritten as secant theta. Okay. So that's how I would do that one. All right, looking at example 3, it says to simplify. I actually think these are a little more difficult because you don't know what you're supposed to get. In the proofs, you at least know where you're headed. Here you don't. When they say simplify, you want to try to combine all the fractions together. Your ultimate goal would be to write it with one trig function if possible and not multiple terms. So I'm just trying to see if I can replace things with something simpler. The first thing that stands out to me here is the 1 plus cotangent squared. I think that that's like one of our identities. So when I scroll back up, notice here 1 plus cotangent squared is equal to cosecant squared. So I'm going to replace 1 plus cotangent squared theta with cosecant squared theta. So this is going to become cosecant squared theta over cotangent squared theta. So then I have to figure out what to do with this. Those of you that are tempted to square root at this point, there is not an equal sign in this problem. You don't know that this is equal to anything specific. That is not something that you can do. 5 is not equal to the square root of 5. You can't just square root a number when you want to. So what I'm going to do here is write these out in their other form. So like cosecant is like 1 over sine. And cotangent is like cosine over sine. And these become like those complicated fractions that we saw before. I'm going to write this up here. Sorry about having to go horizontal here. And I'm just going to write it out a different way. So I have 1 over sine squared theta being divided by cosine squared theta over sine squared theta. And I'm going to actually do this division. So I'm going to multiply by the reciprocal of that divisor. Notice when I do that, I have a sine squared factor that can cancel out, leaving me with 1 over cosine squared. This is good. So I have one fraction here that's gotten down to one trig function, and there's just one more step here because I don't have to write this as a fraction. I actually know something that 1 over cosine is equivalent to, and that is secant. And so this would be secant squared theta. And that would be the simplest way that I could write that. Okay. All right, so there are some simplifying you tries here and some solving. I am actually going to go through them. This is one of the hardest units. Really, the only way you get good at this is taking something, putting it on paper, canceling out, crossing out, erasing. If you're doing this right, then sometimes a problem will mean that you crumpled up a paper 3 times or retried it several times because it's difficult to see necessarily the right answer. So I'm just going to go through a few of these here so that you can see more examples so you get ideas of what you can try when you're working on it on your own. So the first 2 here are simplifying problems. This one has 2 fractions in number 1. If I want to combine fractions together, I need them to have a common denominator. When you see this 1 plus cosine x, don't get overwhelmed. Think about what you would do if it was something with 1 plus x and something with 1 minus x. You would want 1 minus x to multiply 1 plus x to make a common denominator. We want the same idea here. So 1 plus cosine x, I want to multiply by 1 minus cosine x. I can do that even though there's no equal sign here as long as I'm also doing it in the numerator of the fraction. Because remember, now I've taken this first fraction and all I've done is multiply it by 1, but in a weird form where it's 1 minus cosine x. I'm going to do the same thing for the second fraction, but with 1 plus cosine x. So I'm just making common denominators here. So the first fraction will have a 1 minus cosine x in the numerator. And in the denominator, when you multiply 1 minus cosine x times 1 plus cosine x, and some of us will have to go do this on scratch paper, some of us will see the pattern pretty quickly if we can relate it to things we already know, but for some of us the cosine is a little scary there. This is going to be 1 plus cosine x, minus cosine x, minus cosine squared x. These 2 terms will cancel out, and notice we get a 1 minus cosine squared x. Okay. And then we're adding that with the second fraction, whose numerator will be 1 plus cosine x. The multiplication in the denominator is the same, so it will also get 1 minus cosine squared x. Now they can be written as one fraction, where the denominator is 1 minus cosine squared x. And in the numerator, I'm going to add this plus this. So I'm just going to distribute this plus to each of these. So plus 1 and plus cosine x. And you'll see the cosines will cancel. So I will have 2 over 1 minus cosine squared x. But again, having a 1 and a cosine squared together should remind you to look back at that trig identity. So I'm going to go back. I'm going to look at my identities. 1 minus cosine squared can be replaced with sine squared. So 1 minus cosine squared can be replaced with sine squared. And then remember, having a sine in the denominator is the same as having a cosecant. So this is a 2 times a cosecant squared x. Okay. All right, we are going to look at number 2. So number 2 has a lot going on, but a lot going on means you can approach it more from the fact that maybe there's some things you can cancel out and stuff like this. The first thing I'm going to do is write the tangents and cotangents in terms of sine and cosine, since they're multiplying fractions that have sine and cosine in them. So I'm going to think of this as a cosine cubed beta. And remember all these weird things, alpha, beta, theta, they're just Greek letters and they just stand for the angle over sine. And tangent is sine over cosine. And then this term has sine cubed over cosine, and it's multiplying a cotangent. Cotangent is cosine over sine. So I can look at each of these terms and work on multiplication with the fractions to see what happens. So here the sine will cancel. Here cosine will cancel one of those. So I will have still a squared left. So this all simplifies to say cosine squared beta. Here the cosines will cancel. The sine will cancel all but one of those, and that will leave me with sine squared beta. And this is our identity, that cosine plus sine squared should equal 1 since they have the same angle. So that all just boils down to be equal to 1. So the ones underneath this, I know they were still in the category of simplify, I just forgot to change the directions. These are actually proving that they are equal to each other. So we're going to look at a couple of these just to give you guys some ideas of things to try. But you can't watch and learn this. You need to try and learn it, but it's nice to watch at the beginning so you have some ideas of what to try. So in number 3, I'm going to start on the left side. So I'm just going to put an equal sign. I'm not going to write anything over here. I'm not going to ever change that side. Now, there are a couple different ways that we can do this. Notice that this is like a 1 plus cosine theta. This seems kind of close, but I really can't do anything with this. You cannot write 1 minus cosine theta as sine theta. So don't do that. It has to have the squareds to use our identity. Sine squared does have a squared in it, so I'm actually going to try that. I'm going to replace sine squared with what it would be equal to on our identity list, which is 1 minus cosine squared theta, or x. Now, if you're struggling because of the cosine, I want you to take a minute and think about if it didn't say the word cosine in it. If it was 1 minus something unknown squared over 1 minus that something, we're much more comfortable with seeing this and thinking about factoring. When you guys see the cosines, you don't really think about factoring, but you should. This really is the difference of squares, okay? That's like having 1 minus x squared, which would factor as 1 minus x and 1 plus x. Except for it's not x's, it's cosines that are being squared. So that factors as 1 minus cosine x times 1 plus cosine x. Then I can see there is a matching factor in the numerator and in the denominator, and those matching factors can cancel out. And I'm left with 1 plus cosine x, which is what I was supposed to prove that that could be equal to. All right. So I'm going to work on the same thing for the next one. This time I don't feel like I want to factor, and here's why I don't feel like I want to factor. The denominator is just cosine. It's not a 1 plus cosine or a 1 minus cosine, so I don't feel like factoring is going to help me. Notice that the left side has no plus or minus in it. So really for me, I'm thinking, is there a way for me to kind of combine everything here together? Because I don't see any pluses or minuses on the other side. So I'm going to leave the left side. I'm going to work on the right side. And instead of factoring this time, I'm going to see how the identity relates to this. And when you look back at your identity, you should see 1 minus cosine squared could be swapped out for sine squared. Now, the next way that I'm going to rewrite it is really going to be specific towards what I'm getting. Every time I take a step, I'm looking back at my goal. My goal is to get a tangent times a sine. Remember that a tangent, as I'm thinking in my head, tangent is sine over cosine. If I split my fraction that I have up a little bit right now, I can have that. So rather than keeping sine squared right here, I'm going to think of it as sine over cosine, which means I've used one of these and the cosine, times just sine. And that would give me sine squared in the numerator and cosine in the denominator, but then it's really clear that that is the same thing as tangent theta times sine theta. And again, I'm just trying to get you guys some ideas of things you can do. All right. So when I look at number 5, it's a little scary. There's like powers of 4 and stuff like that. I don't know. We could start on either side here and see what we want to do. The only good thing that I'm noticing about number 5, so I'm just trying to give you an idea of what's going through my head so you guys know what to look for. There's tangents and secants, and there is an identity about tangents and secants. So that's good. I just don't exactly see how to use that identity yet here. But I'm hoping that I can flip out, like if I start on the right side, I'm hoping I can get some secant squareds and swap them out with the identity that will change them into tangent squareds. If I start on the right side, I'm hoping I can get some, or the left side, excuse me, I'm hoping I can get some tangent squareds and swap them out for secant squareds. So I think, because I see a secant squared here, I'm tempted just to start on the right side. And then because of what I just said, that I want some secant squareds, I see one in here. But then if I just swap this out, it's going to leave the secant to the 4th by itself still. I want to factor this a little bit to try and break up this secant to the 4th and hope that I can make it lower powers of like squared. And the way I would factor something like this with 2 terms that both have secant in it is I would want to take out the greatest common factor. So the greatest common factor, both these terms have a secant squared. If I factor the secant squared out of the first term, I'll have left 2. If I factor it out of the second term, I still have a secant squared left. So this is actually good because notice that now all of my secants in the way that I've written it here are secant squareds, and I'm going to go look at that identity. Let's see. Here it is. Everything that says secant squared can be replaced with 1 plus tangent squared. So I'm going to go do that. In this problem, I'm going to take every place that I see the secant squared now and replace it with 1 plus tangent squared. So this will be 1 plus tangent squared beta. Then there's this multiplying this 2 minus. Now you have to be really careful. I'm replacing the secant squared with 1 plus tangent squared. I need to put a set of parentheses now that I'm writing 2 things in place of that one thing to make sure this negative gets treated correctly there. Okay, so let's simplify this one a little bit because it looks a little wacky. So 1 plus tangent squared beta is just going to hang out there for a minute. This one has a 2, and this minus distributes to each of these. So 2 minus 1 minus tangent squared beta. And 2 minus 1 can actually be combined together to be 1. So this would say 1 plus tangent squared beta and 1 minus tangent squared beta. So, good thing, I have tangents only. Bad thing, it doesn't yet look exactly like it does, but notice this one has a power of 4. I know a squared times a square can make a 4, so now I'm going to try to multiply these together. So 1 times 1 would be 1. 1 times negative tangent squared beta would be negative tangent squared beta. Tangent squared beta times 1 would be a positive tangent squared beta. And tangent squared beta times negative tangent squared beta would give us that negative tan to the 4th beta. And these middle terms cancel. And then I have what I was looking for to prove that that's correct. Okay. All right, one more. Okay. And so this one actually looks a lot similar to the one that we did before. So you guys, I think, can look at this one, and then we're going to do a couple flip grids this week. I'll post the answer to that number 6 if you guys need it. We're going to do some flip grids this week in addition to your homework. So you're going to have a skill 1 homework, a skill 2 homework, and a skill 2 part 2 to get good practice with identities. But then we're also going to incorporate one problem that you need to video on Flipgrid, whether you get it right or wrong, just so we can get some idea of how you are doing and ideas of how we could solve it.